morning, my dear participants. In the today's class, I am going to explain Euler's theory. Mainly, this Euler's theory is using for the columns. So, which are only we are going to design the columns, that is struts and columns, which are by nature of failure is mainly for the buckling analysis. Okay. The main assumptions by taking this Euler's theory is the column is initially straight. You can assuming that the column is initially straight and the cross section is uniform throughout the cross section, and the line of thrust coincides exactly with the axis of the column. So, whatever that force the line is there, that is exactly coincide with the axis of the column, and material is homogeneous and isotropic. The shortening of column due to the axial compression is negligible, and these following cases may be considered while designing the columns. These four cases are there. One is both ends are hinged, and the second one is one end is fixed and other one is hinged, and the third case is fixed at both ends, and the fourth one is one end is fixed and other one is hinged. These are the four cases are generally we are using for mounting of the columns, and each case how the buckling is taking place and what is the magnitude of stresses are in use, that we are going to calculate. That we will see the one by one. Now, let us see the first case, the both ends are hinged. Now, you can observe this here, these are the hinged points, these 2 points are the hinged. Now, this is the axis of the column, this is line diagram. You can see that the load P is acting along this axis, that load is acting at P, and due to this load, let us assuming that the length of the column is L, and length of the column is L, and due to this load, instead of compressing, because of this length is more, so it will try to buckle. So, now this is the shape of the column, it will buckle, and that buckling will be taking place here. Okay. So, now you can see that the free body diagram of the same. Okay. So, now you can apply the moment, that moment, the P into the lateral distance y, okay, that will be acting in this direction. It causes to move the column in this direction. Okay. Now, by using this Euler the formula, we can find out the what is the crippling load acting on the column, that will be obtained by using this formula. Pe is equal to pi square into Ei by L square. So, here E is the Young's modulus of the column material, and I is the moment of inertia of the cross section of the column, and L is the length of the column. So, this is the for the first case that both ends are hinged. Now, we will see that in the second case, that is one end is fixed and other is free. So, one end is fixed, that means the end is fixed means the degree of freedom in all directions are 0 at that point, that is here. See, this is the fixed. So, the fixed all the degrees of movement is 0 here, and it is the other is free. So, other end is freely, it will be there in the column. Now, applying the load P, now you can see that in this case the load is not acting along the axis of the column, it is away from the axis of the column at a distance A, Now, you can clearly see it in the diagram. Okay. And due to this, what is the crippling load acting on the column, that will be calculated, that Pe is equal to pi square into Ei by 4 L square. So, in this all the formulas, this E and I is same. E is the Young's modulus of the material, and I is the mass moment of the cross section of the column, and L is the length, initial length of the column. Okay. So, the pi square Ei by 4 L square gives the crippling load acting on the column in this situation, that is one end is fixed and other end is free. Okay. Now, you can see that the next case, that fixed at both ends. Now, you can see that at one end and other end both ends are fixed. Okay. Now, the load acting on the column is along this axis of the column. Okay. Now, due to this load, the two moments are acting at the fixed points. Here at this bottom point, the moment is acting in the clockwise direction. At the top, the movement is acting in anti-clockwise direction, and due to these two movements in different directions, the column is tried to buckle. So, that buckle will be taking place, how the buckle, how much that will be obtained, and buckling load you can calculate by using this Euler's formula. The Euler crippling load in this case both ends are fixed is 4 pi square E I by L square. 4 pi square E I by L square. See, in this all the cases you can observe this the formula is the whatever that the variables are same, but only the difference is the magnitude is different in all these three cases that you can observe. So, that according to that position, whether the end is a fixed end or free end or the hinged end, accordingly the intensity of the crippling load will be changes. Now, you can see that last case, that is the one end is fixed and other one is hinged, and earlier you have seen one end is fixed and other is free. Now, you can see that one end is fixed, other is hinged, instead of free it is hinged. Okay. Now, the fixed at the fixed end the moment will be acting. Now, you can see that the moment m is acting in the clockwise direction. Now, at hinged the reaction force is acting in this direction, and due to this there is a chances of buckling takes place in this direction. Okay. So, that buckling load you can calculate by using this Euler's crippling load formula, that is 2 pi square E I by L square. See, these are the 4 cases generally we are observed in any columns, and you can calculate the crippling load by using this Euler's theorem, by using this Euler's theorem. Now, let us see that at a stage all these 4 cases what are the different formulas you can easy to remember in the form of the tabular form. Once you can see that, so that what is the serial number, the 4 cases and end conditions of the column, that is the both ends are hinged and one end is fixed and other one is free, and both ends are fixed, one end is fixed and other is hinged. In both the cases the crippling load in terms of actual length and there is a effective length. Okay, that effective length also you can obtain in this last column, it will give the what is the effective length. So, in the both in terms of actual length, effective length, these formulas are you can see that, and in this case both ends are hinged, that is pi square E I by L square. Okay, thus pi square E I by the effective length is equal to L. So, in here effective length is equal to L. In the second case, that is one end is fixed and other is free. In this pi square E I by 4 L square. So, whereas here equivalent length is equal to 2L. Now, you can substitute here equivalent length is equal to 2L, then this formula is pi square E I by L square, and in the both ends are fixed. In this case, according to the actual length, the formula is 4 pi square E I by L square. So, here the equivalent length is equal to half of the actual length. So, now you can substitute, you can obtain pi square E I by L E square. L E is the effective length, and the last case one end is fixed and other is hinged. This 4 pi square E I by L square, what is the effective length here, that is 1 by that L by root 2. Okay. So, that you can substitute, it is obtained pi square E I by L E square. Now, you can compare these formulas at different cases. Now, you can analyze in which case the maximum crippling load will be there and in which case the minimum crippling load will be there, that we can obtain. Okay. Now, finally, what are the limitations of this Euler's formula or Euler's theory? So, these are the basically the 2 limitations are observed in this Euler's theory. So, there is always crookedness in the column, and these loads, whatever the load acting, that may not be exactly axial direction. Now, we can see that along the axis the load is may not be acting, slightly it is away from this axis, that will gives the and not giving the actual crippling load. And this formula does not take into account the axial stress, and buckling load is given by this formula may be much more than the actual buckling. That is the main the drawback or limitations of this Euler's theorem. The load is not taking along the axis of the column, and due to this the buckling load whatever the calculated, that is much more than the actual buckling load. Okay. So, this is I think I hope all of you understood the Euler's theorem, how it will apply for the columns. So, with this we will close today's session. We will move to the next topic in the next session.